In this last chapter of the course, chapter 10, we're going to investigate geometric series and then look at some applications of geometric series in both the financial world and natural sciences. So first, let's introduce what a series is. A series is an object that adds up a bunch of terms. We're going to be taking a bunch of things, we're going to add them all together. This series can be either finite or infinite, meaning that we can have a finite number of terms, or we can just keep on adding things up forever. Specifically, a geometric series is a series in which each term is obtained from the previous term by multiplying by some fixed value r. And we're going to call this fixed value r the common ratio, as we're going to look at the ratio of one term to another. We'll see that in this first example. So some examples of geometric series, probably the most famous one is what we have here. We have 1, we're going to add 1/2, then 1/4, 1/8, 1/16. This is just a finite number of terms, so we could add these all up using some common denominators, right? We could say this is 16/16 plus 8/16 plus 4/16 plus 2/16 plus 1/16 would give us a total of 31/16. So here the sum would be that value. This is a geometric series, a finite geometric series. Finite because there are just 5 terms there. But it's geometric series because if I take one of the terms and I divide it by its previous term, so like 1/2 divided by 1 would give me 1/2. And if I do that for all of these terms, like 1/4 divided by its preceding term 1/2, I'd get 1/2. If I take 1/8 and divide it by its preceding term 1/4, I get 1/2, and so on and so forth. So what we're doing to get from one term to the next is I am multiplying by 1/2 each time. And then I'm adding those things together. And because I am multiplying by the same number each time, we say that this r value is 1/2. And this is a geometric series. So note this next one is very similar. So this was the first one right here. This next one, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... means that we're going to keep on adding terms forever. So the next one would be 1/32, then 1/64, and we just keep on going forever. This is an infinite geometric series. And here r is equal to 1/2. All right, so different than a finite geometric series because we're just going to keep on going forever, but it's the same kind of idea. The same terms are being used. If we look at the next example, we have 1 plus 1/2 plus 1/3 plus 1/4. So let's see what the value of r is here. So to get from 1 to 1/2, we are multiplying by 1/2. But if we think about this next one, to get to 1/2 to 1/3, we can take 1/3, divide it by 1/2, which would be 1/3 times 2, or 2/3. And then the next term as well is going to be different, but really just because these are not the same, means this is not a geometric series. There is not a common ratio between each term. In the first one, it's always multiplying by 1/2 to get from one term to the next. Here it changes depending on what term you're talking about, which means this is not a geometric series. This is not going to be the series that we're going to be talking about in this chapter. This is a special series. It's something called the harmonic series. But again, it's not going to be geometric, and we're not going to focus on it in this class. The next one is not going to be geometric as well. We can think about how we get from one term to the next. Does follow a special pattern, but this pattern is just subtracting 3 each time. And although that's a series that we could look at, there's something we could say about it, that is not a geometric series. This is something called an arithmetic series, where one term to the next is gotten by adding or subtracting the same amount each time. So you could verify this is not a geometric series by looking at the ratio of the terms, right? The first one would be 7/10, 7/10. The next one would be 4/7. And those are not the same thing, so therefore there's not a common ratio. So this is not a geometric series. Note that this is a finite series. We could think about the actual value of the summation. The one before that was an infinite series. All right, so other than identifying if it is a geometric series or not, we are going to be focusing on solely geometric series for the rest of this chapter. So, as we said before, if we know we have a geometric series, we can find this common ratio r by dividing any term by its preceding term. And we usually use the second term by the first term because that's usually going to be the easiest, but maybe it could be something else. Also note that sometimes we can find this value of r just by inspection. It's very clear when we kind of write it out. We'll see some examples of that in a second. So we're saying all of these are geometric series. Some are finite, some are infinite. Let's just think about what is the value of r, and we're going to think about what is the value of a. So r is the common ratio. And we're going to introduce another term here. This a is going to be our initial value. This is the first term. And we're going to see on the next page why we're going to use that value. It's going to be important when we think about what is the sum of these things. So we already looked at this first one. This was r equals 1/2. And a here is just the value of the first term. That is 1. And note that this is a finite geometric series with 5 terms. This next one here, we can find r by taking any term and dividing it by its preceding term. In this case, we have 2/3. And you could verify that this is our ratio because each term is gotten by the next one by multiplying by 2/3 each time. And that would continue forever. So in this case, r is 2/3, and our a value is 15. All right, so next one here, it looks different. We have 100 in each term. We have 0.16 in most of the terms, gotten to different powers. Let's just verify what is the r value here. If we take the second term, we divide it by the first term, we get our 0.16. And that's exactly what's going on here, is we are multiplying 100 by 0.16. Then we are multiplying by 0.16 again, and that's just, we can write that as 0.16 squared. And we just keep on doing that forever. not forever, sorry. We keep on doing it until we do that about 45 times, and we end with this. So this is actually 46 terms added together, but that's still finite. In this case, R is that 0.16, that's the common ratio. And this is what I say we can kind of get this from inspection. And we're going to see on the next page this kind of generic formula for a geometric series. We'll have this kind of R value to a certain power. A here is also special. A is going to be that 100. It's the first term. And we can see that it's going to be in every single term there. All right, lastly, if we look at the second term, 0.7 divide by the first term, 0.07, we get a 10. Right? Maybe using the 70 divided by 7 is actually easier there. But each step of the way here on this last series, we are multiplying by 10. So here the R value is 10, and the A value is 0.07. And note for this last one, we kind of get into the next page, so we could write this as 0.07 plus 0.07 times 10 plus 0.07 times 100 plus 0.07 times 1,000, do one more, times 10,000. And we could write this 10 and 100, 100 is 10 squared, 1,000 is 10 cubed, 10,000 is 10 to the fourth. And we can say this looks pretty similar to that 0.16 example where we have the A value times R to a different power. So now let's focus on the summation of these things. What does it actually equal when we add these things together? And this is why geometric series are nice, because we do have a nice formula for the value of a finite geometric series. And in fact, we have one for an infinite series as well. We'll see on the next page. So if we have a finite geometric series with n terms, note that if you have n terms, you're going to be going to a times r to the n minus 1s. This is what we did on the previous page. I'm going to go back a second. Take a look at this formula. We have our a value times r to different powers. And that's what we had here, right? We had our a value always times r to increasing powers. And we kind of did it down here as well. We could write all of these in that same way. Note that when we had to the 45th power, that actually represented 46 terms because we start with kind of 0.16 to the 0th power at the beginning. So here's a generic finite geometric series. The initial value is A, the ratio is R, and we can write n terms as A plus AR squared all the way to AR to the n minus 1. And we are going to let S sub n be the value of that summation. If we added up all those terms together, that's our value Sn. We're going to find a formula for this. We're going to show how that works. There's a couple weird algebraic steps we're going to do to get to that point. First thing we're going to do is we're going to take this S sub n and we're going to multiply by R. So we're going to take this A plus AR plus AR squared plus dot 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 plus AR to the n minus 1, which is S sub n. We're going to multiply it by R. So we're taking both sides, multiplying it by R. And this will leave us with Sn, so R times Sn. And if we take R, we're going to have to distribute it to each term here. And if we do that, the power of r is going to increase by 1 in each step. This is going to be ar plus ar squared plus ar cubed all the way to ar to the n. The next thing we're going to do is we're going to take s sub n, what we have in our first thing there, and we're going to subtract r sub sn, or r times sn. So sn minus r sub sn is going to be equal to a plus ar plus ar squared all the way to arn minus 1. And we're going to subtract off ar plus ar squared plus ar cubed plus a sub rn minus 1 plus arn. And when we subtract this, a bunch of these terms are going to cancel out. In fact, everything's going to cancel out except for the first term in Sn and the last term in r sub Sn. So we have total S sub n minus r times S sub n is equal to a minus a r to the n. And if I factor out an Sn, I have Sn times 1 minus r times a minus a rn. And we'll do one more step here. If I take out an a on the other side, we're left with a times 1 minus rn. If we divide by 1 minus r on both sides, we get our formula here at the end. So if we know what a is and we know what r is, we can plug those into this formula, and that will give us the value of the finite sum. And note that we cannot have r equal to 1 here because that would give us a 0 in the denominator. If you tried to find this, you get 0 over 0, and that's an indeterminate form, and that's not good. But providing r is not equal to 1, this is a value of the finite sum. We could also think about the value of the infinite sum by just taking that formula we have and letting n go to infinity. So the infinite sum we're going to let be s, without the n, just s is the sum. And this goes on forever, and this is going to be equal to the limit as n goes to infinity. If we keep on adding more and more terms, if you let n get bigger and bigger and bigger, all the way to infinity, we're adding an infinite amount of terms. So let's look at this limit. S is the limit of s sub n, and we have a formula for s sub n here. All right, so this limit here is going to be a is a constant, r is a constant. And when you take this limit, it's only going to be equal to, the only thing that has to deal with n is this r to the n term. So using some limit rules, we can rewrite this limit as so. A times 1 minus the limit of r sub n, r to the n, over 1 minus r. And what this all comes down to is what is the limit, n goes to infinity, of r to the n. There's a few things we need to do here. So let's first think about if r is equal to 1. If r is equal to 1, actually we should not use 1, sorry, because we know r can't be 1 for this formula. So let's say, what happens if r is less than 1? If r is less than 1, then this limit, we're going to say that r to the n is going to go to 0. The terms are going to get smaller and smaller and smaller if we take them to bigger powers. Think, for example, r equal to 1/2. If r is bigger than 1, then this thing is going to blow up to infinity. Think, for an example, like r equal to 2. 2 to the n is just going to blow up to infinity. And if r is equal to 1 or negative 1, I should say actually, if r is greater than negative 1, less than 0, Rn is going to go to 0, and if r is less than negative 1, Rn is going to go to negative infinity, or is just not going to exist. There's an issue when r is less than negative 1 or bigger than 1. So we're going to say that this limit exists and is 0 if the absolute value of r is less than 1. Which means that this limit here is going to be a times 1 minus 0 over 1 minus r, or just a over 1 minus r if the absolute value of r is less than 1. So recapping all of that on the next page, we say that an infinite geometric series is not always going to be a finite number. All right, and it kind of makes sense. If we add an infinite amount of terms, it may just blow up to infinity. If the value of an infinite series is finite, we say that that series converges. Otherwise, we say that it's going to diverge. So let's look at some examples. In fact, I'm going to start at the bottom and then we'll go to this first one. So if r is equal to 2, that means we are multiplying by 2 each time. We get 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128, on and on and on. This is just going to go to infinity, and this is going to diverge. The numbers are getting bigger and bigger, and we're adding them up. It's just going to blow up to infinity. If we think about r equals 1, what's happening? This is a kind of a weird geometric series. We are multiplying by 1 each time. If we add 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever, that's also going to go to infinity, and that's going to diverge. And for negative 1, that is, we are multiplying by negative 1 each time, which means we are alternating the sign. We'd have 1 minus 1 plus 1 minus 1 plus 1 minus 1. This is going to go to either 1 or 0. And we can't have two values. So this is also going to diverge. It doesn't go to a specific number. So it leads us with our convergent example, this r equals 1/2. And it is kind of weird to think about that if you add an infinite amount of numbers, that the value will be finite. And in fact, we know that this value, in fact, we're going to kind of see what it's going to be. If you use the formula, we can find out what that value is. But let's see why this is finite and how it actually works. And this is going to be why this is called a geometric series. All right, so here we go. We are adding a bunch of things together. We're going to start with this 1. Or we're going to say this is going to be a square of area 1. 1 unit squared. And we're going to take that 1 unit squared and we are going to add a square of area 1/2. Or not a square, but a rectangle, I should say, of area 1/2. So half of the area of our square before. Then we are going to add a 1/4. 1/4 of our original square. Everything about our original square. We're taking 1/4 of that. Then we are going to take 1/8 of our original square, which is half of the 4th. And we're going to add that to our pile here. Now we're going to do a 1/16, which is just taking that, dividing by 2. And we're going to rinse and repeat. So we're going to have a 1/32 there. And a 1/64. And a 1/128. And a 1/256. And a 1/512. And we're going to keep on going. And this total area that we're looking at is not approaching infinity. This is approaching 2 units squared. And there's a nice geometric interpretation of that sum total. If we look at our formula here, if r is less than 1, then it converges to a over 1 minus r. Here, a is equal to 1, r is equal to 1/2. Since that's less than 1, we have 1 over 1 minus 1/2, 1 over 1/2, which is 2. So in order to determine if something's going to converge or diverge, we look at the value of r. If that's less than 1 for an infinite series, we can use this formula. If it's greater than 1, we can just say it diverges. It's not going to be a finite number. So in the next video, we'll look at some more practice problems dealing with geometric series. And then the next 2 videos will look at some specific application problems of geometric series.